Thanks for the invitation to come out here and talk to you. I'll be here for a couple days and hope to have a chance to talk to many of you. I'm going to tell you today about some observations aimed to measure the kinematics of circumgalactic gas. So most of the baryons associated with galaxy halos are not in the galaxy itself, but in the circumgalactic medium. And they're very hard to see. The gas is so diffuse, it's difficult to directly image. And the way we observe this gas and know it's there is largely through quasar absorption lines. So in my dreams, right, we have many quasars sitting behind this galaxy, and I can make a three-dimensional map of what's going on there. We're not there yet. But what we can do, okay, I'm going to tell you about picking a sample of nearby galaxies, about redshift 0.2, kind of similar galaxies that have more or less the same properties, a sample of 50 galaxies that have a quasar nearby behind them. And in the same way that you'd stack images of like objects to get a deeper image, we can kind of think of this as a stacking analysis then of 50 sight lines through the typical halo a few billion years ago, okay? So I think the CGM is really closely related to the problem of how galaxy disk assemble. Okay, this is a picture here from Casey Popovich's paper where it shows kind of the galaxies as a function of redshift. These are real data that would form a Milky Way-like galaxy today. And you can see here, you know, it'll look back time of like 10 billion years at redshift 1.5, 1.6. You already see disk here. Okay? Disks are long-lived, and that kind of 10 gig a year duration that our disk has been around is a little bit surprising, given that if you just take the mass of gas in a disk and divide by the star formation rate, you'd get times more like a few up to 5 or 6 gig a years. So this is one of several pieces of evidence that tell us that disks need a continuous supply of gas to last as long as they do and build Milky Way-like disk. Okay. Now that is until they don't, right? We all know that the other property of galaxies is this division in color, okay, between here what we call the blue cloud, which are mainly late type galaxies, and the red sequence of mainly early type galaxies. And kind of an ongoing puzzle in galaxy formation studies is, you know, what stops the galaxy from forming stars and sends it to the sequence of red and dead galaxies. Okay. And a lot of interest in the CGM has come from this plot. This is a study called COS Halos, led by Jason Tumlinson, who uses a COS spectrograph on HST to study O6 absorption, okay, in the halos of galaxies that are similar to the ones I'm going to tell you about today. O6, because it's highly ionized, requires either very hard photons to ionize it or very high temperatures if it's collisionally ionized. And in this plot, okay, it shows that the detections of O6, knew that was going to happen, are mainly in the blue galaxies. So here are specific star formation rates on this side are star-forming galaxies. These are passive galaxies, okay, that are red with low star formation rates. So the bimodality in galaxy colors also seems to be reflected in the properties of this high ionization gas in galaxy halos. And are the two related somehow has been a puzzle now. I guess it's been seven years now since Jason's paper. Okay. These two samples? That is debated, as well as is this just a color difference or is this also a halo mass difference? Okay? And those answers aren't completely clear. Now, I want to point out that the low ionization gas, okay, in halos, as traced by ions like magnesium-2, that I'm going to talk about a lot today, silicon-2, carbon-2, even carbon-4, it also looks different, okay, in the halos of red galaxies and blue galaxies. And here I'm showing you work from a lot of Sloan galaxies by Lan and Mo, okay, where you see in the blue galaxy, shown by the blue points here, there's an excess of absorption. This is the absorption strength, or the area of the absorption line in magnesium-2 through a halo. And you can see this excess, okay, in the blue galaxies. So what is going on here? And I'm going to focus, okay, on absorption in these blue galaxies in low ions using magnesium-2 to trace it and try to get a better idea kinematically, okay, of what's going on here. Now, one hint that kind of motivated this study is the cartoon I showed you on the cover slide is shown again here from a different author, where there's structure in the CGM, where gas flows into disk with some angular momentum, okay? So it tends to favor kind of the major axis of the galaxy. And galactic winds driven by star formation, well, they make a big super bubble that then blows out of the interstellar medium perpendicular to the disk along the path of least resistance. So in the artist schematic, you get some structure like this for the low ionization gas in the circumgalactic medium. But that's a cartoon, a picture. Does it really exist? Okay, can we see such a thing? And the first evidence really that you could was just looking at the strength of absorption, okay, versus the azimuthal angle, okay? Where here, as you go close to the minor axis, there's an excess of absorption, okay, in purple here. And the green points, okay, are the points closer to the major axis. And this is all as a function of impact parameter, or the distance of the quasar sightline from the galaxy here. So to look at the kinematics, the idea is to have a galaxy that you measure a rotation curve for and a background quasar. Okay. And then you can compare the kinematics from the position velocity diagram that the rotation curve gives you, okay, with the kinematics of the gas you see in absorption in the quasar sightline. Now, this is from a paper that Chuck Steidel wrote in 2002, where he looked at 5 pairs at redshift was 0.6. And in 4 of those 5 pairs, he found that on the side of the rotation curve where the quasar was, the gas was shifted in the same direction as the rotation on that side of the galaxy. Now, the plus and minus here are defining the slit plus and minus. Kind of ignore that. You can see on this end of the slit, the gas in the rotation curve is blue shifted. And then the quasar over here, the magnesium-2 and the magnesium-1 absorption are blue shifted. In 4 out of 5 sight lines, you know, chance or coincidence. And surprisingly, this wasn't really followed up on. Okay? And I should have said in the beginning, the work I'm going to present on these 50 sight lines is in large part the dissertation of Stephanie Ho at UC Santa Barbara. And this has been a huge amount of work to collect this data for 50 galaxies. So it starts out picking a sample of galaxies. And as I said, we're interested in blue star-forming galaxies, so this shows you what it looks like in a color magnitude diagram. I show here just the peak, kind of the central density of the blue cloud where it's highest, and you can see our sample is a little bit bluer than that, just because we had a color cut here to avoid red galaxies. So the halo masses here, right, are something like 10 to the 11 to 10 to the 12. But they're clustered here, you know, in a pretty narrow mass range, okay, about 10 to the 10 solar masses. And we can show that in terms of star formation rate versus stellar mass, where here there's a green line here that's the dividing line between the blue cloud and the main sequence. It's kind of the main sequence of star-forming galaxies here. So we span that pretty well, but our median's slightly bluer. And these are lines of constant specific star formation rate. Okay, so these are the star burst up here, and these are more normal galaxies. Okay. So really, the thing we've done that's fairly new here is to try to work and interpret the circumgalactic absorption in a reference frame of the galactic disk. So what we actually do on the sky, like here's our target galaxy, okay, and here's the quasar. And here's a nearby galaxy on the sky that we don't a priori know what redshift it's at. We drill a slit mask that we take to the Keck telescope, and we get a spectrum of the quasar, a very blue spectrum, okay, that covers the near ultraviolet lines of magnesium-2 that have just been redshifted into the blue part of the optical at redshift 0.2. We get a spectrum of the galaxy. And in this case, the slit mask is oriented, okay, along the major axis of the galaxy here to get the rotation curve at the same time. It's not always possible. And we get a redshift for this nearby galaxy to show that it's not nearby and not a companion to the sky. Okay. So then we have a measured rotation curve across this galaxy. And we define an azimuthal angle that's the angle, okay, from the receding side of the rotation curve to the quasar. So in this example, that angle is 161 degrees, okay, and our impact parameter here to the quasar is about 65 kiloparsecs. And we're going to be dealing with all azimuthal angles and impact parameters ranging from about 20 kiloparsecs up to 100 kiloparsecs. That's about half the virial radius, so this is the inner part of the circumgalactic medium. Now, those coordinates, the position angle, I should step back, from the axis ratio of the galaxy here, we measure the inclination of the disk, okay? And we have a position angle of the major axis on the sky. Those are two coordinates that describe the orientation of the galactic disk on the sky. You'd like to actually describe the orientation of that galactic disk in three-dimensional space, but there's a degeneracy here, right, of these two disks, okay, have the same axis ratio of minor axis to major axis. And a rotation curve in both cases shows you this side of the disk is approaching and this side is receding. So you would think that you can't distinguish between these two flips of the disk that we'll call a positive inclination and a negative inclination. Likewise, if the rotation curve had the opposite sign, okay, there's two more possibilities here. But in fact, you could, if you could resolve spiral structure, okay, in these galactic disks. Usually spiral arms are trailing in a galaxy. Consideration of the angular momentum means leading arms can't persist for long. And with the assumption that most of the arms we see are trailing, you can see how resolving spiral arms in these disks distinguishes between these two signs of the inclination, okay, something we're going to call the disk flip. So an important part of our study, besides getting rotation curves for all the galaxies, was trying to get some high-resolution imaging, okay, to see structure. Now, when we first started taking high-resolution images, we were starting off with Sloan R-band images like this, and it was fortuitous, right, that in the field of each galaxy, we had a bright quasar sitting there. So we could do laser guide star adaptive optics, and these, we took infrared images with NERC2, okay, on Keck. And we had some surprises. This galaxy was two galaxies, okay? Now this didn't happen very often, but there's a disk, okay, right here, and it has a very different position angle and inclination than we would have derived from this image. This case, we found our spiral arms. Now that was a little surprising, nice two-arm spiral pattern here in a K-band image, okay? These are the old stars, probably some sort of tidal feature. This is probably driven by something external. And here's another one where there's some spiral structure, but you can't see it yet.
What happened to the image on top?
What happened to the image on top?
The bottom image has two.
Ah, this galaxy here is right there. It's just with the better point spread function. You can't see it. It's not as blown up. These KS images we were able to get for the full sample. We were able to get Hubble images of 10 galaxies, okay, out of the 50. And in a red Hubble band, F814W, you start to see in this little galaxy, see the spiral arms come out? And then here's the little galaxy that's bright in the red. You can really see the arms here and perhaps a knot out here, something perturbing it. And then in the red here, it still looks about the same. In our blue images, the second object up here has totally disappeared. You can see they have very different colors. And down on the bottom here in the bluest image, it doesn't show up real well, and there's spiral arms right here and here. More like what you'd think, that the spiral arms would be tracing the young stellar population and only be visible, okay, in the F390 image in the blue. So we got our images. We know their position on the sky in every case. And in some cases, we know the 3D orientation of the disk. So let's go take some quasar spectra, right, and see where we can detect magnesium-2 so we can look at the kinematics of the halo gas. So on the left here, we see the sight lines where we detected magnesium-2. And on the right, we see the sight lines where we did not detect magnesium-2. This is in the coordinate system I introduced, where this is the major axis, okay, of all the disk, and the minor axis. And just looking at the distribution, okay, of hits versus the azimuthal angle, that's the solid line here, and the non-detections here are the dashed line. A simple KS test shows you that those two distributions are different. Okay. Here are the quasar spectra. This is the magnesium-2 doublet. Okay, so there's two lines. In the optically thin case, this bluer line will be have twice the area of the red line. I should comment here that we're taking these spectra with a fairly low resolution spectrograph, but a high dispersion grating. So we've got a resolution of only 100 kilometers a second. Okay, and this is a real shortcoming of this study. This is done so that we can use a multi-slit mask and take spectra of other galaxies in the field at the same time to make sure that the absorption we see really is coming from our target galaxy. At higher resolution, some of these lines would be completely saturated in black. Okay? And you can see here structure sometimes. Definitely some of these profiles have separate velocity components, okay, that are blended together into one magnesium-2 system. And we hope to follow up on many of these at higher resolution in the future, but this is our starting point. Okay. Now, this is a paper that Stephanie published last year that focused on a few of the major axis sight lines. Okay, azimuthal angle is less than 30 degrees. And here you go, you've got a rotation curve, okay, across the galaxy here. Looks very nice. And out here at the quasar position, indeed, the magnesium-2 is blue shifted, just like this side of the rotation curve. And if we plot the magnesium-2 velocity relative to the rotation curve, okay, you can see the speed here is a little bit lower. So the yellow marking here shows you the full range of velocity of the absorption. Take that back. The blue line shows you the full range of absorption. See how it just crosses the systemic velocity here. The yellow is a crude attempt at deconvolving that velocity range for the resolution of the spectrograph. Okay? So here's another one. On the quasar side, the rotation curve's redshifted now, and there's a net redshift of the magnesium-2 absorption. And we can keep going here. Okay. Another blue shift and a blue shift. Here magnesium's blue shifted, and yep, that side of the rotation curve is blue shifted, and you see a pattern here. The gas in the halo at distances of 60, 80 kiloparsecs seems to know about the angular momentum of the disk. Now, we don't know where the absorption is along the sight line. It may not be in the plane of the disk. But let's run the thought of experiment and say if the absorption is in the plane of the disk, then I can deproject it to a rotation speed in the plane of the disk and compare that to the rotation curve. And here's what we get. So these are rotation curves. And see here, okay, they've been normalized to the asymptotic rotation speed, and the radius here has been normalized to the virial radius. Okay? So the rotation curves kind of all pile up on top of each other then. And then these are the absorption velocity ranges in the quasar sight lines. If you were to draw a line out here at kind of a constant rotation speed, you can see I'm stumbling on what this color is. I think on this projector this is teal. Okay, the teal points are somewhat below the predicted rotation speeds, okay, at this radius. Now, a better predictor of the rotation speed from a halo model, okay, is these red squares, and still the teal points are below the red squares. So the gas is co-rotating, but if it is in the disk plane, it's not moving quite fast enough to be on a circular orbit everywhere. Okay? So maybe it's in the disk plane and slowly spiraling inward with a radial component, or maybe it's just not in the disk plane, or maybe it's a warped disk, so the geometry is not quite right here, but something's going on. So these were the major axis sight lines within 30 degrees of the major axis, and we said, okay, we've got to take this a step further and look at larger azimuthal angles. Yes?
What about some non-rotational, but like some galactic fountain type of geometry that would introduce additional velocity components and lower your...
Yeah. So we're going to see a signature of outflows in this data. I think we don't see outflows at these low azimuthal angles because there's so much co-rotation.
I think you plotted angular momentum, not circular velocity. That stuff has much, would appear to have much more angular momentum than it did. Because it's at, 3 times the radius or something, and it's only slightly more.
We will compare it to the disk shortly, the angular momentum.
Okay. For those of us who are not
Yeah, sorry.
What do the simulations say about the potential at the radii where this gas is seen? Should it still be, should the circular velocities, in theory, be the same as that of the disk out there?
So the models, just using a Navarro-Franken-White halo model, okay, they say the circular velocity should be right where these red squares are.
Well, I'm assuming more of all these dark matter simulations have been done.
Yeah.
So
oh, in an actual sim. Yeah. At the end, we're starting to look at the Eagle simulations a little and compare directly to this, but I can't show you that right here. Okay. So let's go back and see if we look at more quasar sight lines at increasing azimuthal angles. How far away from the major axis can we get and still find this co-rotation? So here's the same coordinate system, major axis, minor axis. The color coding now is that things that are red, okay, have a Doppler shift in the same direction as the galactic disk. If it's blue, it's got a Doppler shift in the opposite direction. We call it counter rotation or reverse rotation. And if it's white, the absorption at our resolution is indistinguishable from the systemic velocity, which really means the Doppler shift's less than about 15 kilometers a second, and we can't say anything. Okay, and I think even before we do any statistical test, you can see kind of in this area, everything we can measure is co-rotating. And this corresponds to an azimuthal angle here of about 55 degrees.
You said shifted by less than 15 kilometers a second?
The white points, if the Doppler shift of the magnesium-2 system was, say, 8 kilometers a second, that's smaller than our error bar on our velocity measurement. Okay, so we can't say if it has a net Doppler shift, and I've just colored it white here.
It's not surprising to find that many points that have Doppler shifts that are so small compared to systemic velocity.
The white ones?
Yeah.
Well, in a naive model of the circumgalactic medium, I would have said, gas is just falling in from everywhere. It's spherical. Everything's on random orbits. And I would have expected every point to have, the mean of the absorption components would come out to be near zero, that there would be no net angular momentum.
But
there would be dispersion, but all I'm plotting here is the equivalent width weighted mean velocity.
Or a single, what is there,
A single sight line. But a single sight line, when you look at simulations, is intersecting many separate streams of gas. In some models for the CGM, where the cold gas is literally a fog that's kind of condensing out of the hot phase, many, many particles would contribute to the absorption, and there should be no net Doppler shift. If there's streams and you're hitting 2 or 3 structures along the sight line, then yes, it's going to move around some based on the velocity dispersion of the halo. Yes, we'll be there in a minute. So here's the co-rotation. And I think I've said all this. Just I'll point out along the minor axis here, there's basically an equal number of blue and red points, okay? Minor axis, no co-rotation. We tried to compare the statistically, okay, again, the KS tests, the distribution and azimuthal angle of the co-rotators, and the reverse rotators is very different. We also thought of this in terms of like the binomial distribution, and if you get co-rotation, that's like getting, flipping a coin and getting heads twice, or flipping 2 coins, right, and having them both come up with the same sign. Heads and heads, they're rotating away from us, tails and tails, they're rotating toward us or whatever. And either way, you get that there's only a few % chance, okay, of finding this many co-rotators. Okay, so I'll make a shift now from the sign of the velocity to the strength of the absorption. Okay, this is a little bit getting at the question that Eve asked. The absorption strength, okay, depends on azimuthal angle. This is something that's pretty much every study of magnesium-2 has shown for the last several years. Okay, this is not the first time this has been seen. And again, in this same coordinate system, the points here, okay, are color-coded, and the symbol size now both represent the absorption strength. Okay, so I'm sorry, there should be a key up here. Color has a different meaning now. Red here, okay, means the very strongest absorbers in our system. For those in the absorption line field, these are equivalent widths greater than an angstrom in the 2796 line. And they all lie at very small impact parameters here, kind of toward the major axis. Probably here we've directly intersected disk. In kind of the 0.3 to 1 angstrom range, we've got the blue points here, which are skewed toward the minor axis. And this is the result, the skewing toward the minor axis that's been seen several times before. This excess near the major axis is new. And I think it's because even compared to some studies that have had many hundreds of sight lines, they had very few sight lines at these small impact parameters. So this is probably direct detections of things we would actually call disk as opposed to extended disk, warped disk, streams feeding disk, okay? But this excess toward the minor axis, okay, in just the strong 0.3 to 1 angstrom absorbers is very real. This shows equivalent widths versus impact parameter here, where the color coding, is different impact parameters, and this is versus azimuthal angle. If we bin those, okay, the blue here, the blue points here, you can see this increase, okay, toward the minor axis. Okay, and these are the red again is the red points here, the very low impact parameters.
How big is the optical disk on that scale approximately?
I'm going to try to deproject this into the disk plane in just a minute. We're not quite there yet, because I want to separate kind of what we see on the sky from then the interpretation that this comes from the disk plane, because that's a major leap there, okay? So let's look at this major axis okay, this is really bad. somehow these two labels got switched. Okay, we're in the same coordinate system we were before, minor axis, major axis. Sorry about that. The excess equivalent width toward the minor axis. To look at that closely, we've got to take out the dependence of the equivalent width on impact parameter, right? As the sight line gets further away from the galaxy, it's well known that the lines get weaker, okay? So we're going to use this relationship from Nielsen's paper, okay, to normalize the equivalent width we see in a sight line. Just divide it by the expected equivalent width at that impact parameter. So large symbols here are equivalent widths 2 times the expected equivalent width at that impact parameter. And small symbols are half the expected equivalent width. And what you see is all, except for this guy out here, all the great big points out here where there's an equivalent width excess lie along the minor axis. Now, why is that? Well, large equivalent widths in this case, these are strong absorbers. These are saturated lines, okay? So a high equivalent width means there's got to be a large Doppler parameter. But we're not measuring Doppler parameter here in the sense of the local velocity dispersion of the gas. We're measuring something more macroscopic, either the turbulence in the gas or, at this resolution, probably kind of the velocity dispersion between different components. Okay, this is a macroscopic velocity spread that we're measuring. So I think the right interpretation here, right, is that there is a kinematic disturbance in this area that's roughly 30 to 45 degrees from the minor axis. The sizes? Yeah, we have a KS test I can show you. Yeah. You know, it's not a 10 sigma result kind of thing, but at the 3 sigma level, it is significant. So here are the equivalent widths, okay, in magnesium-2 versus the Doppler width, okay, of the magnesium-2 absorption, the velocity width. And the coding here is by impact parameter, okay? So at low impact parameters, white, we have strong absorbers and large equivalent widths. But you see these two things are very correlated. So what I'm suggesting, right, is that we think about the excess of equivalent width along the minor axis as increased velocity spread. That can come from the gas being stirred up more turbulence, or it could come from there just being an extra velocity component in some sense that makes the whole system broader. Okay? And to take that a step further, I'm going to, of course, argue, okay, that this disturbance is galactic outflows and winds. I'm going to show you a couple examples, the cleanest cases, of course, where I think the magnesium-2 absorption is dominated by the outflow. And it's really purely a geometric argument, okay? So Fiducial outflow model is that the disk stops the superbubble in the plane of the disk, and we get this bipolar outflow. We're going to have a coordinate system here, x, y, where the disk is in the xy plane, the z-axis is perpendicular to the disk. And then our sight line, right, is going to be along some plane in a plane parallel to the y-z plane. And the intersection of that plane with the cone, right, is going to make 2 parabolas. And then our line of sight through there to the quasar can intersect this parabola, okay, usually at 2 places. And we can look at that for a couple examples here and see what sort of velocity range a wind could make. Okay? And we've got at this stage, I'm trying to show you that the outflow is plausible. Okay? And there's a fiducial model here for the outflow that's based on observations of galaxies, where in galaxy spectra, okay, we see blue-shifted resonant absorption lines, pretty much in all strongly star-forming galaxies, that are interpreted as outflows. And their opening angle is kind of 30 to 45 degrees, and the Doppler shift's around 100 kilometers a second. And I'm going to use that as the fiducial outflow, show you the absorption it would require, and not do any fitting here. Yeah?
Just so I'm clear, is the idea that the outflow is on the surface of the cone or filling the cone?
Therein the question lies. Okay, I'm going to show you the full velocity range along the sight line through the cone and the 2 endpoints. And that's one of the things we'd like to eventually figure out from these data. But we're not going to get there today, okay? So here's an example, okay, of one of the galaxies. And again, okay, hint of spiral arm coming out here, spiral arm coming here. Okay, stretch your imagination a little bit, it's there. So we get the 3D orientation of the disk. The background map here, okay, shows the velocity field from the rotation of the disk, okay? And these ellipses are the disk, okay? These are different radii in the disk, 100 kiloparsecs, 80 shows you the tips of the disk. Here's in the color contours here, that's like the spider diagram, okay? You've seen 21 centimeter maps. And this is the receding side of the disk, okay? And the approaching side, and here's your velocity scale from rotation projected onto the line of sight velocities. And then here's our little toy model of a disk with the right orientation of the arms, and the back side of the wind's going that way, and the front side of the wind's coming toward us, and here's our quasar sight line. Okay, so using the coordinate system from the previous slide, this is with a outflow opening angle of 45 degrees, and this is 30. And you get a little red-shifted gas right at the edge of the cone here, and then this is blue-shifted. And then over the cone here, this one's blue-shifted. The 30-degree cone, you get this range of velocities in purple. The wider cone, you get the range in cyan. This is compared to the absorption profiles here, okay? Solid line's 2796. The other black line is the 2803 line, and it fits the blue-shifted gas pretty well. In comparison, in this sight line, because it's so near the minor axis, there's very little projected rotation speed, and that's shown by the dotted line here, which is kind of right on the edge of the profile. Not surprising that you don't see a disk here, given that in terms of disk radii, right, this is out here at like 150 kiloparsecs, okay? So I think that's a pretty good case for an outflow. Here's another one. Okay, again, we just barely got those arms, but it works. Here's our geometry, but now the sight line's on the blue-shifted side of the rotation curve, but red-shifted wind. Okay, same game. We expect red-shifted outflow now, okay, across the sight line. Here's the prediction. Okay, it's over on the side of the absorption trough, but look, rotation from a disk is way over here. We could tune the wind speed down a little to move this over. Maybe there's a little bit of a component from a disk too that would come up at higher resolution, and the two are blended together. After all, the sight line here is at a radial distance in the disk of 60 kiloparsecs. So probably two components there blended together. Okay, and just one more. There's an arm. Here we go. This is out a little over 100 kiloparsecs. Okay, maybe a little something from a disk component over here by the dotted line, but the main component, okay, is blue shifted, okay, and coming from this wind. So things we can say without making assumptions that then drive a more physical model, which is where I'm going next, okay, are that there's this distribution of Doppler shifts that's correlated with the rotation of the disk, and it completely rules out a model for the low ionization CGM kinematics where the motions are random, okay? It's just out. And we can say that the CGM, okay, whether it's in a disk or not, clearly there's significant angular momentum in this low ionization component. And if you're going to come up with some schematic model for the CGM, it better include that angular momentum. Okay? So going forward here, we're going to explore axisymmetric models for the rotation, starting with a thin disk, see where it works, where it fails. And then the other result here, right, is that there's some kinematic disturbance that we see along the minor axis that seems to be related to a galactic outflow. But I think there's a major question here that I'm not going to have an answer to today of whether this disturbance is cold clouds being transported out to these distances, or whether this is a disturbance of the CGM created by a hot wind that left the galaxy and hit CGM, okay? And I'm sure with several of you we will discuss this more this week. So let's see if we can get a little away from what's been mainly a geometrical argument, okay, towards something that's a little more physical or measuring physical parameters. And this will involve more assumptions, okay? Here's just a simple model, okay, for rotation on circular orbits in the disk plane. We can use that, okay, to predict the line of sight velocity field that we would see around this galaxy. Okay, so this box here corresponds to the little red box here. And I'm saying if this thing is surrounded by a huge gas disk, based on the rotation curve here, here's the velocity field it would have along the line of sight. And in some cases, the quasar position is such that, you know, it intersects that disk. Again, these are radii of 20, 40, 60, 80, 100 kiloparsecs at places where, okay, plausibly a disk there. It's a very large disk at tens of kiloparsecs. In other sight lines, though, okay, this galaxy is more inclined. This is out here. In the disk plane, this impact parameter is 400 and some kiloparsecs. Okay, so probably not going to be intersecting a thin disk out there. But, you know, what about here, where it's a little over 100 kiloparsecs? Where do these disks end? Okay, so we've tried to look at this and ask the question of, let's go a step beyond is the gas co-rotating, because we see no end to that in terms of impact parameter, and say, given the rotation curve, could we be so bold as to predict the Doppler shift that you will see magnesium-2 absorption at? Well, the answer is it depends where the sight line hits the disk. So in this plot, we've got the projected velocity of a disk versus the measured magnesium-2 Doppler shift. Okay? And the color coding here is now by the impact parameter, but not on the sky, but translated to the disk plane using the geometry I showed you. Okay? Assume the absorption is in the disk plane. And what you find is that the lighter colored points here, the things that are white, for example, have impact parameters at less than 70 kiloparsecs in the disk plane. Among the white points here, okay, there's a correlation. This is the Spearman rank order correlation coefficient, 0.42. That's about a 2.2 sigma result, okay, that the two things are correlated. So it's not exact, okay, but they're correlated. As you go out and include sight lines, like in black here, that intersect the disk at large radii, closer to 100 kiloparsecs, there's basically no correlation at all. And this is showing you how that correlation coefficient increases, okay, as the radius in the disk plane gets bigger. And it kind of goes up and flattens out around 80 kiloparsecs and then starts to fall. So this is the best rough estimate I've got at the moment of how big this co-rotating structure is that seems to be somewhere near the disk plane. Okay, about 80 kiloparsecs. Yeah?
Sorry, are the two plots showing, or the text in the bottom and the plot on the right showing the same R?
So this is showing you all R, color-coded here. And here I'm increasing, I'm starting just with the white points and calculating a correlation coefficient. And then I'm going out to increasing radii and watching the correlation coefficient increase. And then it kind of hits a maximum here at 80 kiloparsecs, and then it levels off and starts to fall. No?
So then, okay.
No?
You're just saying for the large sight lines, there's no correlation with the
The correct statement here would be that it's no longer improving. And if you, well, okay, the correlation here is staying there because it includes the inner points. If you just look at the black points, if you can somehow focus and make the light points disappear, okay, there's no correlation with just the black points. Here it's cumulative, and that's why something persists.
How
Yeah.
does the scale of 80 kiloparsec relate to the virial radius of the galaxy?
A little less than half the virial radius in these. So this is, our largest sight lines are at about half, and most of these are 30 to 40% of the virial radius. So the plot I promised you, projected back into the disk plane now. Okay, these are new axes. This is not on the sky now, but in the disk plane, X and Y. These are constant radii in the disk plane. Here's this 80 kiloparsecs. And now I'm showing you this equivalent with excess again. Again, this is the stuff that I think is winds up here and has nothing to do with the disk. Important here, I've showed you with X's the sight lines where we did not detect magnesium. And within kind of 70 kiloparsecs here, you know, only in one case is there a non-detection. Point of this is that the covering factor of magnesium-2 is very, very high, close to unity, when the sight lines intersect the disk within about 70 to 80 kiloparsecs. So with those radii, there seems to be some contiguous structure there, whereas the co-rotation at larger impact parameters might be more due to tidal streams or something. Okay.
Is there any reason for the sampling?
Yeah, it looks funny, doesn't it? Yeah. Partly here, this is not the sampling on the sky. This is the projection onto the disk plane. The sampling is more uniform on the sky. The original sampling of the quasar sightlines is completely uniform on the sky. There's also some variation in covering factor of magnesium with azimuthal angle, so that distorts it a little, and then when we project it to this plane, it gets very distorted. What you're mainly seeing here is that along, if you're asking why do these points show up, when you take a disk and tilt it, and you have a minor axis sight line, you will intersect that disk plane at very, very large radii, okay, because of the cosine I. So that's why all these points come up here.
And there are no points at all? Are the observations on the x-axis going to 160 or not?
In our data set, no, but you could fill this in easily, okay? Probably even using data in the literature if you went back and got the rotation curves for the galaxies. This is, out here is where the studies have been traditionally done. Having the sight lines close in the inner part of the CGM is what's newer. Okay. This is coming back to a diagram I introduced earlier. And I was making the point, right, that the gas is not moving quite fast enough to be on a circular orbit if it's in the disk plane. And here we just kind of tried to say, okay, if we conserve angular momentum, okay, and this gas spirals in toward the center of the galaxy, when does its speed kind of get up to a circular orbit? And that's what these cyan curves trace. And this stuff would meet, a lot of the material meets the disk kind of at the edge of the disk or a little bit further out. This is our plausibility argument, okay, that this is gas that is indeed feeding the outskirts of the disk, okay, and contributing to the inside-out growth of disk.
Does that make sense? I mean, given the amount of magnesium and some reasonable metallicity, should I think of this as representative of the bulk of the gas, these radii, or is this embedded in the visible hotter component that has much more mass, and so it's moving in its viscous medium?
Right. This is a great debated question, you know. We could get into a whole hour-long discussion here about the relationship of this low ionization gas to, say, the oxygen-6 gas that's being traced, to, say, gas actually at the virial temperature. And the water is murky here, okay? There is a picture where, you know, this gas and the O6 are co-spatial. And I've got an extra slide at the end. There might be time to pull up. There's some kinematic correspondence between components you see in low ions and absorption components you see in O6. On the other hand, the equivalent widths in O6 seem to fall off much slower than they do in the low ions. And there's an interesting paper Jonathan Stern wrote a few months ago that would argue that because of this difference in the equivalent widths with impact parameter, that the hotter gas and the low ionization gas cannot be, that the O6, let me not say hotter, the O6 and low ionization gas are not cospatial. And then all this kind of boils down to arguments about where you think the accretion shock is. Okay, if it's really out at the virial radius or twice the virial radius and all the stuff is inside, or in Jonathan's picture, the accretion shock's at half the virial radius, and the O6 is actually a photoionized component that's out beyond it. Yes, that's the question, right? What is the right schematic here? And what I can say here is that based on this rotation, one of the next questions we want to try to answer is whether the intermediate gas, okay, traced by the O6, is co-rotating or not. And there's a recent paper just a week or two ago by Glim Kapsak suggesting it's not, although in the two cases here where we can test it, in the one where we see co-rotation in magnesium-2, we actually see co-rotation in O6 as well. Sorry, that was a long-winded answer to say this is muddy, okay?
What about the hydrogen gas?
What about the hydrogen gas? You know, the hydrogen gas is a different beast in some ways because when you observe it along the sight line, the peculiar motions from stuff falling in make you see the hydrogen along a much longer path length. So you see a lot of stuff that kinematically is similar, but it may be well beyond the virial radius, whereas the metals tend to trace stuff inside the virial radius. So I think this is the better way to isolate the inner halo.
Does this diagram assume that you're seeing only gas at the tangent point, or could you also be seeing other gas that's further out that would have a lower velocity and thus bias those points?
Yeah. In this particular diagram, we assume it's a thin disk and it's at that tangent point. In this paper, Stephanie explored thick disk, okay?
I'm talking about radially. More gas at a higher radius than the tangent point, having lower velocity and thus shifting the centroid of the profile to a lower velocity than that at the tangent point.
So yes, I mean, one way to look at that, I mean, you could look at that effect in a purely spherical model. We didn't do that because of the co-rotation. So we said, okay, look at just a cylinder, okay, that's rotating to get the co-rotation, but make it thick. You can even add some, velocity gradient, as would be seen like in the ISM in the Reynolds layer or something. And you can broaden the lines that way. So there's kind of in making the lower velocity gas, you can take your thin disk and make it thick. Okay, and then your sight line, as it goes through that disk, will start to see gas at radii where you're not at the tangent point, okay, and that'll give you these lower velocities. Your other option, okay, is to take the thin disk and add radial inflow. In other words, besides the rotation speed, just make, sorry, that's the wrong plot. Just add a radial inflowing component, okay? Making the disk thick so that the sight line's not just at the tangent point, and adding radial inflow in a thin disk largely do similar things, okay? It's hard to distinguish. And Stephanie spent some time looking in cases where you know the disk flip, could you perhaps distinguish? And just to show you an example, this is where she nicely took some of those images in different bands and combined them into a color image. You're supposed to say woo here. You see the spiral arms, and this gets kind of technical, okay? So I don't want to put you to sleep with this, but let me just illustrate what you could do, okay, with this type of data going forward. When you look at a thin disk model here, okay, this is along the line of sight through the galaxy, the projected velocity. The black line here is the range of velocities from just the disk model. It's to be compared with the shaded cyan region, which is the measured range of velocities. And you can see here the thin disk, it misses all these velocities here for the absorption. And you can say, if I add radial inflow, can I get absorption at those velocities, for instance? You can do the same thing with a thick disk model. But in this case, there's a way to distinguish. So the point is that what the radial inflow does depends on which way the disk is flipped. For a positive inclination, okay, it adds like this, and you can only add a fairly low radial inflow speed of about 100 kilometers per second here before you'd push the summed component beyond what's observed. If you have a negative inclination, okay, you can add a much larger radial inflow, almost 500 kilometers per second, because it's got the opposite sign from the circular component in the disk. You get these intermediate velocities, and you could produce the full velocity range here. So we've got a prediction in this one example where if it's radial inflow, okay, describing this full range of velocities, the disk has to have a negative inclination. And then we go and resolve the spiral arms, and we see the disk has a positive inclination. So we can rule that out. Okay? In this case, it's not radial inflow. Is it a thick disk? Maybe. So let me finish up here just turning to simulations a bit to say, can we get some insight about what's going on? These are some plots from the fire simulations, paper by El Badri. This is very much the inner part of the CGM. The scale bar here, okay, is just 5 kiloparsecs. These are gas column density is cut off here at about 5 by 10 to the 19 per square centimeter. Okay, so this is gas you would see in 21 centimeters. And the point of this is there's a lot of stuff here, if you look at the velocity field, right, where you'd see net angular momentum and co-rotation with the disk, but you wouldn't necessarily call these things disk, okay, in the traditional sense of a thin rotating structure. Stephanie has started working with the Eagle simulations to look at how galaxies, galactic disks, get their gas in those simulations. And this is kind of a neat plot where she's taken this Eagle galaxy and color-coded the gas particles by the time it will take them to reach the inner disk. Think of this as an accretion map, where purple things here are already in the disk. Things in green cannot reach the disk on a dynamical time scale and feed it. This is just a simple, take the particle, just treat its trajectory ballistically and see if it gets to the disk. And the points in red kind of fall into the disk within a rotation period of the disk. So she's identifying here gas in the simulation that could feed the disk in kind of the next generation of star formation. And this is a plot of the angular momentum of these gas particles versus their radius in the galaxy. And you see a bunch of stuff kind of in the disk along this black line. And then the infalling points, okay, are down here. They don't have quite enough angular momentum to stay where they need to be. Okay. So I'm going to skip over that detail, I think, and just say, again, a lot of this is motivated. Okay, this is back to data now for nearby galaxies. This is a histogram of gas consumption times in galactic disk from an old Kennecott paper. And these time scales, right, really are just a few million years. We can go all the way back to the G-dwarf and M-dwarf problem in the galaxy to explain the paucity of low metallicity stars. You've got to keep feeding the gas with relatively low metallicity gas to make lots of higher metallicity stars and dilute that population. Okay? So we can take away from this CGM's got angular momentum. The CGM has been disturbed by winds, and we can see this distinction. As we start to model this in detail, on case-by-case bases, I think we can start to get information out about radial inflow speeds, perhaps, or gradients in rotation with the height of more cylindrical structures, or in the case of outflows, we'll be trying to get to a map kind of what the velocity of this cold gas is as a function of its radius, which can help us distinguish, okay, what the relevant physics is for creating that cold component. Thanks.
Thank you for this very nice lecture. We have time for a few questions.
Yeah.
Could we tell if the oxygen 6 occurs more in the thing that is co-rotating at the middle major axis or in the outflow material?
So you should hire Stephanie Ho. This is exactly what she's proposing to do for her postdoc project. Okay. Here's what I know today. I'm not gonna answer that question. Okay. But here's what I know, okay? You can just go look at some of the absorption profiles from COS halos, okay? And you look at the data, you're amazed. Like in blue here is the oxygen 6. See, it's all on one side of the systemic velocity. I would have expected the O6 to be kind of symmetric, okay? And there's some kinematic correspondence here, right, between O6 and low ions. Look at that in those two components. So the oxygen 6 is not a kinematically simple thing. So we went and looked in the archive. Okay, 2 of the galaxies out of our 33 magnesium-2 detections had an O6 observation in the HST archive. Okay, here's one of them. This is our magnesium-2 profile. This is the carbon-2 profile from the COS spectrum. You can see the difference in resolution I've been telling you about here. Here's the O6. So this was a magnesium-2, a co-rotator, and the O6 is co-rotating too. And I said, this is crazy. And I talked to Jonathan Stern, who wants to put the O6 out at large radii, okay, in this shell around the galaxy. And I said, there's no way that gas out there is co-rotating. Jonathan said, oh, yes, it is. And this is his snapshot from a fire simulation where this is O6 absorbing gas out here. Can you see it here? There were supposed to be there's little velocity vectors on here. But this stuff, in the fire simulations, the O6 is in streams of stuff that are falling in. And Jonathan says it will be co-rotating. Oh, here, I zoomed in on that. Let's go one more. Now you can see the little arrows. See, it's not random. Now, that picture, okay, is completely different as far as I can tell from all the hydro simulations out there. This is an example from Eagle and Ben Oppenheimer's work, where the O6, was out here filling stuff out to the virial radius instead of John's picture. And then Glenn Kapsak posted a paper last week or the week before, where he started to look at co-rotation of the O6. He says it's not co-rotating. He wants to attribute it all to winds. Well, I told you in our sample there were 2 galaxies with a HST spectrum. The second one was one of the minor axis sight lines in an outflow galaxy. And I looked at the data, and the oxygen 6 is not even detected. But that's 2 sight lines. Glenn's paper has many more sight lines and concludes the O6 is not rotating. So that's the answer today, but I don't think it's a settled question.